So this is joint work with Simon Fox, who is doing his PhD with me. But because he's a student, he's very poor, he needs to earn his lunch and food. So he's behind the camera. And even a bit late. So I will present this alone. So you all started last year, and Lara was presenting an algebraic approach for time reactive programming. And Brent Yoge was there, and he had described, I knew his work on diagrams, and some other people were explaining a bit of 3D specification, drawing your programs. And I told Brent I could use our tiling staff to do program, and he told me no, because the way we were tiling things, we were catching things only by one point, one instance in time, so it was not wide enough to do drawing. So I told myself, okay, let's see. And a year after, we are actually tiling the whole spatial temporal space, and we are doing animation, 3D. So the plan of the talk is the following. I will start with a preamble that is a glimpse of the future. UK is not known or renowned for the quality of its food, but it is definitely renowned for the quality of its filmmaker. And Terry Gilliam is telling us what will be the future. I will show that. What will be the future as sort of a wish. Then I will describe as an opening how the turtle can move with its pen, and then the first theme, the monoid semantics behind the turtle. The funny thing is that we are setting up rather abstract tools to describe semantics that are applicable to very simple language, like the Logos turtle, which is good. This leads us to the notion of recitable monoid that has some property, and then we can give the turtle a violin, or more concretely, we can allow the turtle to play in time, and we have actually this semantic can just be lifted with time, and it is 2D, but actually we can do it 3D, and there is plenty of not necessarily easy reading things in the paper here and there about some technicalities about algebra. I will try to keep it light. Especially I will stop talking about inverse monoid, because I talk about it so long that either you already know what is an inverse monoid, or I already told you already twice and you still don't know. Perhaps I should give up. So okay. And after that, because we also told ourselves it would be fun to show the result. It is sort of a DSL, there is a demo, but perhaps it will be shorter than as planned in the program, because we had a very tough and interesting day already. Okay, a glimpse of the future. According to Terry Gilliam in this movie, Zero Theorem, that it seems that I'm the only one that ever saw that movie, because I see nobody agreeing that. Okay, so this is a programmer office. And this is a programming device. Yeah. That's a gamepad. And this is a program. And the guy in the movie is constantly trying to put cubes together. And when his programs are correct, he's happy, and some liquid goes into a tube, and that's the program he can send to the main computer. And when it's wrong, then everything collapses, and he's desperate. And there is sort of a Curie-Howard-Gilliam correspondence between program, proofs, and building, and programmer, prover, and builder. And if we think about it a second, it is long known that geometry and mathematical fact in geometry already bears a lot of what is a proof, what is a statement, etc., etc. So perhaps Terry Gilliam is right, saying that in the future, programming, we know that in the future programming will mean proving, because we know that correspondence. But these proofs will be made 3D or even more. So that's sort of a wish and a dream. And it's true that as soon as you're programming graphic things, then checking whether it's correct or not, well, you watch the graphic, and if you want to make a ball, and it's sort of a web like a hedgehog, you know that your program is incorrect. Without debugging. Okay. So the turtle and its pen. It's amazing the success of Logo just for the turtle. This is a pity because it seems that it's full of feature programming language. But anyway, so here is the Logos turtle. It has a pen that can be moved on and off the screen. When it's on, it makes a dot. When it's off, it doesn't. And it can move. And when it moves with the pens down, then this draw a line. And when it moves with the pens off, then it doesn't. And it can move backward. Actually, not Logos turtle, but ours. It's a bit more powerful. You will run 3D actually, and so on and so forth. And the turtle can turn. Already I said it can move backward, but it can even turn. And so you walk one, turn, walk one, turn, walk one, turn, and you've made a square. It's even possible to make a circle. It's a bit hard. You need to know a bit your mathematics to draw a circle with the turtle. Drawing 2D figures or more. So the elementary action of the turtle we take are the flip that moves the pen on and off. It's more comfortable than putting the pen down or putting the pen off, because then I don't need to handle the state. Flip is reversible. I can walk for some distance, or I can turn for some angle. And of course, I should have distinguished the type of distance and angle, but for laziness issue, we're using the same type. Later, this type D will even be time. So here is an example of a program. Walk one, turn pi over 2, perhaps it would be better 90 degree anyway. And, so this draw a square, provided you start with the pen down. So programs are sequences of comment. So there are strings. So programs form a monolith. So if we look for a semantic of Logo program, we want a monolith. And if I ask you, give me a monolith semantic of Logo program, you will probably very easily make one. But I want to understand what is the mathematics behind. So you'll see our monolith will be a bit indirect, slightly more complex, but then generalizable. So first we have position in state. Positions are, in fact, position in the space, the 2D space. Then orientation, an angle, modulo 2 pi, and then a Boolean, pen up, pen down. And we have also figures that are drawings on the plane, and I consider figures to be some subset of the plane, the elements that are black. And although the language describes in a single comment, any comment or most comment of the turtle, there are actually two distinct things. Yes?
Figures are 2 times R2.
Okay, no, sorry, here I'm drawing segments. You're right, you're right. This is segment, so from one thing to another thing, which means that two identical drawing may have several representations. In fact, I don't care. That was perfectly true.
Maybe only if it goes backwards.
Sorry?
There will only be duplicate ones if it's the exact same segment that's going the other way.
I will come to that. This will be a very important property. On the screen, it's just the same. The drawing will be the same, even if the turtle goes backward. So there are actually two kind of behavior of the turtle a move, because it goes from one position to another position, eventually changing orientation, moving pen up or down, and drawings. From the start position, the turtle make a drawing. And the most common of the turtle are actually a combination of moves and drawing. Okay? So what is this, we want the semantic to be compositional, which means that the semantic of the program should just be the concatenation of the semantic of each command. And what will be so I will describe two semantics, the move semantic and the drawing semantic. The move semantic goes from position to position. A flip just changed the position of the L. Here it should be P, there is a typo. A walk change the position in the space with adequate sinus and cosinus because there is some angle. And the turn change the angle. Okay? There is the drawing semantic. The drawing semantic makes the following thing. In some state, if I flip this state, if I run into, so I change the, perhaps here I could have put actually absolutely no drawing at all. This is just a bit of noise, so let's forget about this. So here I'm saying that if the pen was on, then it's marking the point. But if the pen was on and I was here, probably the point has been marked already. So actually it's sort of no drawing at all, flipping. And then a walk, add in the set of drawing, no actually from what I'm saying, a walk from a position I want to create a figure. So if I walk from a position, then I just create the one segment figure from the initial position to the position I reach. And a turn create no figure at all. Okay? And this will combine, so the element of my monoid will be actually pairs of moves and figures that are parameterized by starting position. And it's not that clear that that this defines element of a monoid, but in fact, yes. Or do I combine two such pairs of move and drawing? I'm trying to use the word M for move and the word D for drawing so that we don't get lost. So the combination of these two pieces of program of the turtle are, I first do the first move, M1, then I do the second move, M2. I do the drawing from the initial position defined by the first program I execute, that one, so D1, and I add to this the drawing that I will make with the second piece of program, but from the position reached after executing the first piece of program. So I need to add here the move of the first program right before the drawing. And the union here, so these actually function from position, so the union is the union of the function from position, or the pointwise union, which is rather clear. And as soon as an algebraic sees this, then this is recognized as a semi-direct product of monoid. So, I'm going perhaps slightly too fast. What is now the semantic of a program? The empty program is doing nothing, it's the empty semantic. The empty semantic, yes, actually it's not defined here, but I don't move and I draw nothing. This will be the empty semantic. And the program of the semantic of a program starting with an action A and continuing with the program B will be the semantic of that action combined with the semantic of the program with this operator.
The empty program has the identity.
The identity
effect on the position and yields the empty figure.
Yes, definitely. Which, by the way, are the natural element of moves with flip composition and of drawings, as it is usually the case in semi-direct product. So here, we are happy because the semantic is actually a morphism from the free monoid generated by elementary action, so just strings of elementary action into the semantic monoid that is described here. Okay? So, then series of observation, moves under flip composition form a monoid. If they are reversible, they even form a group. Who cares? Or we'll see. Doesn't matter. Drawings under element-wise union also form a monoid. Well, because behind I have my drawings that are, it's a power set, so I can make union of sets, and then I function from position to sets, so I can also make the union. So it's a monoid, it's even idempotent and commutative monoid. And moves, acts by endomorphism on drawings by this action. So if I have the action of a move on a drawing is just performing first the move before making the drawing, and that appeared there, this action. And in fact, the semantic monoid I showed you with this combination rule, this is exactly what is called the semi-direct product of the monoid of move by the monoid of drawings. And well, I'm happy. You perhaps not. You're telling yourself, what pedantic presentation of the semantic vector. You might be right. This monoid, so you go on Wikipedia, look for semi-direct product, you will find this definition. So there are still some more things available here. We can define, given a program, I can define the reset here not on the syntax, but rather directly on the semantic. I keep the drawing performed by the program, but the move, there's no move at all, the identity function. So this is transformation on the program I can have. And, okay, I'm babbling a bit, sorry. Okay, so this is generally available, okay, as soon as you have a monoid acting by endomorphism on the lattice. So these things actually have plenty of theoretical property. I will list them quickly, and then next slide I will give you a computational interpretation of this reset. So there is this reset that I can write like this. I reset the move to the unit. Here is the identity. And it has the property that if I consider all the resets, then it is a sub-semigroup that is actually isomorphic to my lattice. Why the lattice? Oh, perhaps I'm going a bit fast. Because a semigroup that is idempotent and commutative, this is actually a lattice because you can interpret your binary operation as a meet. Then you have an order. And either you know that, you tell yourself, of course. Otherwise, you don't know. That's no problem. You can have a look later, think about it, or not. That's fine. And then it has hopefully a lot of property. It is known by the York School, a school or some subdomain of algebraic semigroup theory developed by John Fontaine and many more. It is known as the left semi-adequate monoid. And it has even more property. You can wonder what is the equivalence induced by this reset, and so this equivalence has some property. It is left harassment, it is left restriction. Restriction, for those who are doing category theory, this is known. There are restriction categories somewhere. They have been invented by that guy, Harassment. Harassment was a French mathematician of the mid of the 20th century. So plenty of property, but let's forget about them. What is the reset? What is the meaning of a program? I reset my program P, and right after I compose my program Q. It actually means I send the turtle performing the drawing of the program P, but I stay in the same position, and myself I perform Q. So this is a fork. And I don't care about the behavior after the turtle make the turtle I sent make the move and die. Okay. So with violin, perhaps I should go a bit faster because I only have 5 minutes. So Let's do the same with time. I have temporal move from time to time, whatever is the time, or let's say it's the reals. And I have animation. Animation are function from time to, well, my states of turtle that are making drawings, etc. And I can compose these temporal, I can compose temporal move and animation just the same way, because time transform do act on animation the same way moves on the space we're acting on drawings. So I have the same structure. This is still a semigroup, and that's it. I have a semantic for animation.
What's an inverse monoid?
This is
Part two.
this is stronger than recitable. It's in the case the monoid here is actually a group. I can always move back, and this gives more property. An inverse monoid is something that you can. It's actually always like this. So you can always move back, but what you have drawn stays there. So it's a mixture of a bit of group, you can move back, and a bit of idempotency. Whatever you have outputted stays there. And this schema appears a lot in computer science, so in programming. So I guess it could be more used for semantic. You may think that I'm weird to look for a similar project there, but I was discussing with Edward Kmet, who is perhaps also quite a weird kind of programmer, because he knows a great deal of category theory. And as soon as he's doing memory access, he's actually thinking in terms of similarity product as well. The move is where you need to move in your memory so that you have free space, and drawing is writing in memory. Okay, so with this semantic, I can define sort of generically on this sort of time monoid, delay, stretch, delay that push later in time the drawing, stretch that make it faster, start or stop. For it, I need to go to partial function, but anyway. And okay, let's talk a bit about our actual implementation. So we eventually make a 3D animation program. The idea is that the pen of the turtle now becomes a curve. A circle, a square, a gear, and as it moves in space, it creates a surface. And if we have time, then it creates animation. And so extrusion is a bit, we change a bit the semantic. The turtle is somewhere with some pen, moves, not making any drawing, arrives somewhere else, define the new pen, and then says connect. And this is easier because if you want to draw a circle, you are somewhere, you go to the center, you turn, you go to the point and connect. And then you make the connection. In Logo, if you want to directly write a circle, you need to remember what is a cosinus or a sinus. And personally, it is always taking me half an hour. But okay. So now we used some Haskell library, but either they turned to be just wrong or to be hard to learn. So we eventually decided to directly play on the GPU, which means that we don't, for the underlying DSL, we actually don't have a syntax because, it's a bit by default. We do have a semantic here, and we send the semantic on the GPU, and we do everything on the GPU for rendering. And efficiency, we can send on the GPU 5,000 elements. It can create 1 million of triangles. Let's divide this by 10. And we can do that at decent animation rate from 30 to 70 frames per second. Here is an example of a scene that we draw with this language. Here are the triangles that are actually so the skeleton of the underlying scene, and What is very interesting when you are doing computer graphics, this is well known for these people, is that you can, when you are drawing surface, there is something that's important, what is the normal of the surface. So this gives you a vector, you can take the color of that vector in the RGB space, and this gives you this drawing so that you know whether or not your drawing or your surface computation is correct. And plenty of things. It's hard for me to swallow, but it is available on the web, it's public. This is my first program ever on the web. Unfortunately, Simon was there to make it slightly better, but still, and well, there it is. Thank you very much. We can perhaps stop here, and I will make a little demo after some questions if there are. Thank you. Yes.
You mentioned in passing that you could have had an inverse to make it a group. That didn't seem to be something that interested you that much, but it seemed like it was actually quite an interesting way to extend mathematics to have a total erase or something like that.
So, if moves are a group, then I can always make a move backward, and then I have what is known to be an inverse semigroup. That has a little more property than this resettable semigroup. But in fact, these resettable semigroup are more than enough. Why so? If you want to make a drawing with a turtle, you can move a bit, you can define your drawing as a tree-shaped thing. You go somewhere and then you send the turtle down there, and then the reset always allows you to go down to the last position or something like this. And this is very useful to draw scenes, because a scene in 3D graphic is generally a tree. And so you move with some, or it can be, there are other techniques that can be better. It can be a tree. You move by some space transformation, and then you want to define the drawing corresponding to all subtrees, and these trees can be encoded by resets. And it is known that this resettable monoid can encode trees. So it's enough.
Okay.
Yes?
I was wondering if you could use this technique to do some kind of analysis of programs, like to show that two turtle drawing programs create equivalent drawings or something.
So to decide about the equivalence of logo program, yes?
Sure, yeah.
So as far as the semantic is giving the semantic equivalence, so the mapping between. So two programs are equivalent if you have the same semantic. And
So are there well-known algorithms that can...
so the semantic is computable, and then I would need... Okay, checking that two drawing functions are equivalent, are equal. This.
It's not two drawing functions, it's two drawings, so it's straightforward. There's no decision making in the turtle, so.
Yes, you're right. From any position,
you can normalize the points.
Yes, yes. So up to the fact that a single segment can be cut in two, which make a bit of mess. But yeah, essentially these are very simple program anyway. There is no input. It's a lot more messy with input. Yes?
I played around with this operator with turtle graphics too, and had a lot of fun with it. And there's another one you can make, which I called fork, so I'm having trouble. But what it does is, it makes a second turtle that evaluates one expression, and the first turtle does not. And then from then on, all the turtles do whatever the commands are that come next.
Yes. Yes. Yes.
Single instruction, multiple turtles.
Yeah. SIMD turtles. Yes. Or
SIMD.
SIMD.
It's rather MIMD. But yes, this is possible, and there is a way to play with this. It's essentially the same, because anyway later you will only synchronize behind one, not the other, or otherwise you have to keep reference. I don't. But okay, yes.
So the first part of the talk was two-dimensional. Okay.
Yes.
then suddenly you went 3D. But how does a turtle make a triangle?
This is why that I tried to explain. It doesn't make triangle, it directly makes a face. The pen in the 2D thing is a point. And the turtle is sort of already doing extrusion. So it make a point and moves and stop. This is a way of painting. And then you lift up, you go back, move a bit, up. And that way I'm sure you can, actually in Logo that was real robots making drawing. And so for 3D, instead of having a single point, you have a curve on, say, the XY axis. And you move by arbitrary 3D transformation, rotation, translation, symmetries, why not? Whatever. And this makes your curve move. And so you create a tube. Or do you make a ball from a tube? One point, a bigger circle, the equator, and then you move down, and then you have sort of a... So there is a problem of brushing the ball that may arise. Okay? I will make some demo of drawings anyway. Yes?
So, since you have this monoid, is there any kind of, it's somehow linked to the plane, is there some sort of homomorphism to the wallpaper groups or the Euclidean groups, the symmetries of the plane? Have you explored that at all?
I would like to answer. I am a novice algebraist, I am a novice mathematician, I am a novice programmer. Don't ask too much. Perhaps you're right, we should discuss about it, but it could be, yes, of course.
Because it seems like
algebra
the
is such
sort
a
of,
powerful tool.
the moves are the sort of translation operations.
Yes, and rotation, and actually, I turned 3D just by moving also in the other dimension.
Yeah.
That's it. Okay, perhaps you can.
The last question, otherwise we can move to the demo part of the...
We will move to the demo part.
Okay.
Okay.